Have you ever stopped to think about how a simple pebble thrown into a lake can teach us so much about the universe? That circle that spreads across the water isn't just beautiful, it reveals one of nature's most fundamental behaviors, wave propagation. What's most curious is that this doesn't just happen in water. The sound you hear, the light that illuminates your room, even the signals that keep your phone connected. All of this happens because there are waves traveling around, all the time. But what exactly is a wave? It seems like a simple question, but the answer opens doors to understanding everything from how your hearing works to the secrets of cosmic background radiation. Science shows us that waves don't carry matter. They transport energy and information. They vibrate, propagate, and transform. In this movement, they create much of the reality you perceive. They also create the part you don't even notice. But there's an important detail here. Many people confuse waves with movement. Although they are connected, not every movement is a wave. That's why in this video, we're going to dive into oscillatory movements, wave characteristics, their types and properties, always with practical examples, simple analogies, and some surprises along the way. Understanding waves isn't just a physics exercise. It's a powerful way of seeing the world. So if you've ever had the feeling that everything vibrates, that everything is in constant motion, you might be about to discover why. Get ready. The journey through waves is just beginning. Imagine a pendulum swinging from side to side, without hurry, without stopping. This type of movement, which goes back and forth around an equilibrium position, is what physics calls oscillatory motion. It happens periodically, meaning it repeats over time, as if obeying an internal rhythm. But don't think this only appears in old clock pendulums. This behavior is everywhere, from a vibrating spring to the particles that form atoms. What makes this movement so special is precisely its regularity. Whenever there's a restoring force, oscillation happens. The restoring force is the force that pushes the system back to equilibrium. Think of a spring attached to a mass. If you pull and release, the spring tries to restore the initial position, and the mass keeps going back and forth. Gravity is also a classic restoring force, as in the case of a pendulum. This type of oscillation is so predictable that it's even used to measure time. Old and modern clocks still rely on this principle. This oscillatory pattern appears in surprising places. In biology, for example, heartbeats follow an oscillatory rhythm. In engineering, vehicle suspension systems use principles similar to the mass spring system. Even tides, with their regular rises and falls, resemble periodic movements. Studying this type of movement isn't just theoretical curiosity, it's understanding how the most diverse systems in our daily lives work. It's true that not every oscillation is perfect. Friction and other resistances cause the amplitude to decrease over time. Even so, the pattern remains visible for a good while. It's like a dance that's losing energy but not the step. When energy is constant, the movement can last indefinitely. This is the foundation for many instruments, from musical metronomes to vibration sensors and structures. Oscillation is in everything, even when we often don't notice it. Every oscillation has a kind of signature, its own identity, that can be described by some fundamental characteristics. The first of these is the period, which indicates how long the system takes to complete a full cycle. If we think of a pendulum, for example, the period is the time it takes to go to one side, return, and come back to the initial position. Each system has its own rhythm, influenced by factors like mass, length, or stiffness. Along with the period, we have frequency, which shows how many cycles occur per second. It's the inverse of the period and is measured in hertz. If something oscillates with a frequency of 2 hertz, it means it's completing 2 cycles every second. The higher the frequency, the faster the vibrations. In sound, this defines whether it's higher or lower pitched. High-pitched sounds, for example, have high frequency, while low sounds have lower frequencies. In visual terms, frequency relates to color. High-frequency lights are more bluish, while lower-frequency ones lean toward red. Frequency is, in many ways, the wave's identity. Another striking characteristic of oscillatory movement is amplitude. It represents how intense or energetic a wave is. The greater the amplitude, the more energy it carries. In sound, this translates to volume. A wave with greater amplitude sounds louder. In light, it's connected to brightness. In other words, even without touching, a wave can impact us with more force depending on this characteristic. If we were to represent all this in a graph, the most common format would be the sinusoidal graph, full of crests and valleys. Each crest represents the highest point of oscillation, and each valley, the lowest. This pattern is so universal that it appears from electrical signals in electronic devices to heartbeats on hospital monitors. Understanding what this graph represents is like deciphering the language of oscillations, a language spoken in laboratories, satellites, and even in nature. When you throw a stone into a lake, what happens? Waves form and spread, right? But notice, the water itself doesn't go along with the wave to the shore. What actually moves is a disturbance, a vibration that spreads. This is exactly what science calls a wave, the propagation of an oscillation, without transporting matter, but with energy transfer and often information. Matter vibrates locally, and this vibration propagates. This means that where there's a wave, there's also a transmission mechanism. In the case of water, it's the liquid surface itself that conducts the vibration. In sound, it's air. In light, it's the electric and magnetic fields that vibrate. Each medium has its way of allowing the wave to move forward. It's as if nature invented 1,000 ways to pass messages without needing to carry objects. Just vibrations that spread. The beauty of this is that waves are everywhere. When you hear music, you're receiving vibrations transformed into sound. When you see colors, it's because electromagnetic waves reached your eyes. When you talk on your phone, what travels isn't your words, but signals that were converted into waves. Modern life is literally a dance of coordinated vibrations, going back and forth between devices, bodies, and environments. All of this started with simple movements, like that pendulum we mentioned before. It oscillates, and if there's a medium to transmit this oscillation, a wave is born. This is the bridge between oscillatory movements and the world of waves. A bridge that transforms local energy into long-distance communication. Knowing what a wave is means understanding how information travels. Whether in a conversation, a sunbeam, or a signal from deep space. Waves aren't all the same. There are different types that vary according to the medium, the direction of vibration, and even how they propagate. The most well-known are mechanical waves, which need a material medium to exist. Think of sound waves, waves that form on a string or on a lake's surface. Without air, water, or string, these waves simply don't happen. That's why in space, where there's no air, sound doesn't propagate. Mechanical waves can be one-dimensional, like a string vibrating back and forth, or two-dimensional, like on lake and puddle surfaces. Sound is an example of a three-dimensional wave because it spreads in all directions from a source. On the other hand, there are electromagnetic waves, which don't need a medium. Light, microwaves, radio signals, and even X-rays fall into this category. They propagate even in vacuum, carrying energy through space. Another way to classify waves is by observing the relationship between the direction of propagation and vibration. In transverse waves, like vibrating strings or light, vibration happens perpendicular to the direction of propagation. In longitudinal waves, like sound or the movement of a compressed spring, vibration and propagation follow the same direction. This distinction helps understand how different types of energy behave when traveling. Knowing how to identify the type of wave isn't just theory. This influences how we build musical instruments, microphones, speakers, and even how we design earthquake-resistant buildings. After all, understanding whether a wave is longitudinal or transverse, mechanical or electromagnetic, completely changes how we deal with it. Knowing these variations is the first step to mastering the language of vibration, a language that's behind practically all modern technology. When two waves meet, something curious happens. If they're aligned, meaning peaks and valleys hit at the same instant, we say they're in phase. This makes the two add up and create an even more intense wave. It's called constructive interference. But if they're misaligned, one with a peak where the other has a valley, they can cancel each other out. In this case, we have destructive interference. Phase is like the rhythm of a dance. If the steps match, energy adds up. Phase difference is precisely this mismatch between two waves. It can be small or large, but it completely changes the result of the encounter. Think of two people pushing a swing. If they push at the same rhythm, the movement increases. But if one pushes when the other is pulling back, the movement stops. With waves, it's the same. Phase difference determines whether they'll collaborate or compete when they meet. A simple analogy to understand this is time zones. Imagine two cities have synchronized clocks. They're in phase. Now, if one is 3 hours ahead, there's a phase difference. One city's wave will be ahead compared to the other. This type of comparison helps a lot when we're dealing with signals, especially in technologies like radio, radar, or even satellite communication networks. Mastering the idea of phase isn't just important for engineers and physicists. Sound systems, for example, depend on this to prevent sound waves from canceling each other. Poorly positioned microphones at a concert can create regions where sound literally disappears. In telecommunications, phase and signal go hand in hand to ensure transmission quality. Understanding this dynamic opens doors to manipulating waves with precision, whether to improve a signal or to neutralize noise. One of the biggest confusions that arise when talking about waves is thinking that they carry objects from one place to another. In reality, waves don't transport matter. They only cause local vibrations that propagate along the medium. Imagine a buoy floating in the sea. Waves pass through it, but the buoy doesn't go to the beach. It goes up and down in the same place. It's the movement that travels, not the water itself, nor objects on it. This concept might seem strange because to our eyes, sometimes it looks like the wave pushes things forward, especially when we see ocean waves breaking on the beach. But something different happens there. When the wave hits the coast, it stops being a wave in the physical sense and transforms into flow. In other words, the energy that was vibrating converts into real water movement. Only then is there matter displacement. This wave behavior is fundamental to understanding why sound energy doesn't move air to your ears. It's the vibrations it transmits. Similarly, visible light that reaches your eyes doesn't carry particles from the sun. It's fields vibrating in vacuum that bring energy here. Knowing this changes how you interpret the world. You stop seeing things moving and start seeing energy patterns propagating. Precisely because of this, waves are so powerful. Without needing to move mass, they manage to transmit information, heat, sound, light, and even feelings, like music that moves you. By understanding this subtle detail, you gain a new lens to observe everyday phenomena. This prepares the ground to explore the next levels. How wave physics connects with areas like quantum mechanics, optics, and communications technology. Getting to this point, it's clear that oscillatory movements and waves aren't just classroom concepts. They're the foundation of almost everything that happens around us, also inside us. From the tick-tock of a clock to how an antenna works, from the sound we hear to GPS functioning. Understanding these phenomena is like learning to read the universe's source code, which expresses itself in vibrations, rhythms, and patterns invisible to the eyes. Notice that although oscillatory movement is something local, like a spring going back and forth or a pendulum swinging, it can give rise to a wave that spreads this energy through space. This distinction between what vibrates and what propagates helps understand complex phenomena more clearly. A vibrating string generates sound. An oscillating electron can generate light. A seismograph detects Earth's vibrations. The principle is the same. Everything starts with an oscillation. The more we dive into this topic, the more it connects with other fields of science. Acoustics, optics, electromagnetism, and even quantum mechanics. They all dialogue with the language of waves. The universe, it seems, vibrates at different frequencies. Some audible, others visible, and many still beyond our perception. This leads us to reflect. What else is vibrating out there that we still can't detect? Now, the question that remains is, what are you going to do with this knowledge? How can you apply this new way of seeing the world in your daily life? Pay attention to sounds, lights, patterns that repeat. Maybe you'll start noticing there's a symphony of vibrations happening all the time. If this content helped you see further, don't forget to subscribe to the channel and hit the bell to keep following our next dives into the universe of science.